A new study in Nature Neuroscience proves that 2-month-old babies are already secretly categorizing the world around them.
Which is wild.
It is. So our mission for this deep dive is to unpack this stack of fascinating recent studies to uncover the hidden intelligence of infants. We're going to explore exactly how scientists actually manage to read babies' minds and, reveal what this means for you in your own parenting journey. So welcome.
Yeah, welcome. And, to really grasp how monumental this new discovery is, we kind of have to look at the historical hurdles of infant research first.
Okay, lay it out for us.
Well, for decades, the main way we tried to figure out what was happening inside a baby's head was through eye tracking.
Which, sounds straightforward enough on paper. You show a baby a picture and track how long they look at it.
Right, but trying to get a 2-month-old to participate in a strict scientific study is, well, it's essentially like trying to interview a sleepy potato.
A sleepy potato is perfectly accurate.
And there's this great study published in PLOS, one that perfectly details the sheer physical hurdles here. The researchers were trying to capture baseline eye tracking data in 2.5-month-olds, and they just laid out the anatomical nightmares involved.
Anatomical nightmares, like what?
First, you have the total lack of muscular control. Babies under 6 months just cannot consistently sit upright and their heads flop around.
Right, which is adorable for a parent, but an absolute nightmare for a precision camera trying to lock onto a tiny pupil.
Exactly. And it gets much more complicated than just a wobbly head. An infant's eyeball is physically smaller than an adult, so there's less surface area for the camera to measure. And then there's the famous chubby cheek problem.
Okay, yes. The chubby cheek problem is my absolute favorite scientific hurdle. Let's unpack the physics of why a baby's cuteness actively sabotages scientific equipment.
It's so funny. So standard eye trackers use infrared light, right? They shine this invisible light to illuminate the pupil and create a reflection on the cornea, which the camera then tracks.
Okay, makes sense.
But in early infancy, the area right below the eye socket is filled with a huge volume of periorbital fat.
In other words, those intensely pinchable chubby cheeks.
Exactly. And evolutionary biologists actually believe those cheeks exist to trigger a cuteness response in adults, making us want to nurture them.
It's a brilliant survival mechanism, like be cute, get fed, survive.
But that exact survival mechanism physically obstructs the infrared cameras. The fat actually pushes the lower eyelid upward, completely blocking the line of sight for the tracker.
Wait, so the camera literally can't see the bottom half of the eye?
It cannot.
Yeah.
And when you combine that structural blockage with the fact that newborns spend about 80% of their time completely asleep,
Right.
you can see why gathering reliable data on what babies are looking at has been so profoundly frustrating for scientists.
Okay, so if eye tracking have these hard biological limits, how do we look deeper? Because if the eyes are blocked by cheeks, scientists realized they needed a bigger, much more powerful tool to see what was actually happening inside the brain itself.
Yeah, they had to go straight to the source.
Which naturally leads us to the radical new approach here, putting awake 2-month-old babies into MRI machines.
Right. And this was the really ambitious goal of the Nature Neuroscience study, led by researchers from Trinity College, Dublin, and Stanford.
Stanford, okay.
They didn't just want to scan a handful of babies either. They set out to scan the brains of 132-month-old babies. And the critical factor was they needed to be awake and actively watching a screen.
Okay, I have to push back here on behalf of every parent listening right now. If you've ever had an MRI, you know they're basically loud, claustrophobic tubes.
Oh, they're terrifying.
And the number one rule is that you have to stay absolutely perfectly still. How on earth do you get a 2-month-old who has literally zero physical self-control to lie motionless inside a booming magnetic tube without having a catastrophic meltdown?
Well, the researchers knew strapping them down would cause instant distress, right? So they came up with this really ingenious, cozy setup that prioritized comfort. They put the babies on special custom-made beanbags inside the scanner.
Beanbags, okay.
Yeah, it allowed them to recline snugly, sort of simulating that secure, enclosed feeling of being swaddled.
So it's basically the ultimate high-tech nap pod.
Basically. And to manage the noise, they gave the babies special sound-canceling headphones to muffle those loud knocking sounds from the MRI.
Okay, that makes sense.
So once they were settled and awake, the researchers placed a large screen directly above them inside the scanner. And for 15 to 20 minutes, this screen played these vibrant, colorful videos featuring 12 different categories of everyday things.
Like what kind of things?
We're talking dynamic footage of cats, trees, ducks, shopping carts, just moving shapes. Dr. Cleona O'Doherty, the lead author of the study, actually described the immersive setup as IMAX for babies.
IMAX for babies? I
Yeah.
mean, that paints such a vivid picture. Just reclining in a beanbag,
Yep.
completely immersed in this giant screen. But before we get to what the researchers actually saw, let's clarify the mechanism of the scan itself.
Sure.
Because when we say they're scanning their brains while watching these videos, what is the fMRI actually capturing? Because it's not like it's reading a ticker tape of their thoughts, right?
Right, no, not at all. fMRI stands for Functional Magnetic Resonance Imaging. What it's actually measuring is blood flow, specifically the uptake of oxygen by cells in the brain.
Okay, oxygen.
Yeah, the brain is incredibly greedy for energy. When a specific part of the brain fires or becomes active in response to something you see, like a cat on the screen, those local brain cells demand more oxygen to do their work.
Oh, got it.
So the fMRI detects those microscopic, localized changes in blood oxygen levels. And this lets researchers map exactly which neural pathways are lighting up in real time.
Okay, so we have this IMAX beanbag setup. The machine is tracking the oxygen, rushing to different parts of the baby's brains, and they are watching these videos of cats, ducks, trees, and shopping carts. What did the blood flow actually reveal?
Well, the resulting scans completely defied expectations. Scientists just did not expect this level of cognitive maturity.
Wow.
Even at just 2 months old, the baby's brains were firing in distinctly different, highly organized patterns when they looked at an animate object, like a cat or a duck, versus an inanimate object, like a tree or a shopping cart.
At 2 months old,
Yeah.
they can't even reach out and touch a cat. Their arms are still just basically flailing around.
Exactly.
Yet their brain is actively categorizing the world into living and non-living buckets.
The neural signatures were remarkably distinct. The biological machinery required to separate the world into complex categories is already functioning. And to verify just how sophisticated these neural patterns were, the researchers actually turned to artificial intelligence.
Wait, AI. How do you map a digital AI to a biological baby's brain scan? What's the actual mechanism there?
So they utilized deep neural networks, which are these advanced AI models trained on vast amounts of internet images to recognize and categorize objects.
Okay.
They ran the exact same videos the babies watched through the AI. Now, an AI processes images in distinct computational layers, right?
Right.
The early layers identify really simple things like edges and contrast, while the deeper layers synthesize those edges into complex concepts, like actually recognizing a cat. So the researchers mathematically compared the activation patterns in the AI's layers to the localized blood flow patterns in the baby's brains.
Basically overlaying the digital map onto the biological map to see if they matched up.
Yes, and the resemblance was striking. The baby's localized brain activity mirrored the highly sophisticated later stage layers of the AI models.
That's insane.
It is. The infants weren't just processing basic visual static. Their visual cortex was organizing the information with the same structural complexity as an advanced machine learning algorithm built specifically for categorization.
Okay, let me see if I can put this into a real-world analogy. It's almost like the baby's brain is working in a mailroom, right?
Okay, yeah.
It's already sorting all the incoming mail into living and non-living folders before the baby even knows how to read the addresses on the envelopes.
That is exactly it. The categorization system is built and functioning way, way before the scientific community believed it was even possible.
Which is an incredible breakthrough just on its own.
Yeah.
But as we kind of comb through the research here, finding these sorting folders online at 2 months old actually creates this massive paradox about how the human brain develops. It kind of upends a fundamental assumption we've held about learning, doesn't it?
It really does, because the fMRI scans pinpointed this categorization happening in a region of the brain called the ventral visual cortex.
Ventral visual cortex.
Yeah, and that's a very high-level processing area responsible for complex visual recognition. But the paradox showed up when the researchers looked at a different part of the brain called the lateral occipitotemporal cortex.
And what does that part do?
That's the area responsible for processing basic, low-level shapes, lines, and contours. And in these 2-month-old babies, that low-level shape processing area showed no reliable signal whatsoever.
Hold on, let me make sure I'm grasping the magnitude of this. How can a baby's brain know the complex category of a thing, like knowing it's a cat, if their brain cannot even reliably process the basic physical shape of the cat yet?
I know, it sounds impossible.
It's like knowing a book is a mystery novel without being able to see the individual letters printed on the pages.
That's a great way to put it. It's the ultimate mystery novel paradox. And it directly challenges the traditional bottom-up theory of cognitive development.
Okay, define bottom-up for us in this specific context.
Sure. So for a long time, the assumption was that brain maturation is strictly hierarchical. We assumed infants first had to learn simple features like lines, edges, and basic shapes in the lower level brain regions.
Right.
Then eventually, those simple shapes get passed up the chain to higher level regions to be assembled into complex concepts, like identifying a category. Like you said, learn the letters, then read the word, then understand the genre.
But this study proves development is totally non-hierarchical. The complex categorization in the ventral visual cortex is coming online before the basic shape processing in the lateral areas is even fully established.
Exactly.
Why would the brain develop out of order like that?
Well, researchers have a really compelling theory about this. The lateral regions of the brain, the ones responsible for detailed 3D shape perception, likely require motor skills to fully develop.
Oh, interesting.
Yeah, think about it. To truly understand the physical shape and boundaries of an object, you need to be able to reach out, grab it, turn it over in your hands, manipulate it.
And a 2-month-old definitely lacks the motor skills to grab a toy and inspect it.
Exactly. So that physical interaction with the world might be the missing biological trigger needed to unlock that specific part of the visual cortex. But even without that physical interaction, their ability to conceptually categorize the world is already highly active.
Wow.
They aren't passive observers waiting for their bodies to catch up. They are dynamic thinkers constantly trying to make sense of the visual data flooding their system.
Well, so if they are these active dynamic thinkers at 2 months, but they can't grab things yet, are they actually mentally connecting the dots of what they see? Because this actually connects directly to a classic study from the UCLA Baby Lab.
Oh, yes, by Scott Johnson and Richard Aslin.
Right, looking into something called object unity. Let's talk about that.
That UCLA study is such a crucial piece of the puzzle here. So to test if babies understand that hidden parts of an object are connected, the researchers set up an experiment using a monitor. They showed 2-month-old infants a display featuring a long rod moving back and forth. However, the center of the rod was hidden behind a solid, stationary box. So all the baby could physically see was the top of the rod and the bottom of the rod moving in tandem, with a big block obscuring the middle.
Got it. Now, if a baby's brain is purely processing what is physically in front of them, they should just see 2 disconnected floating pieces of a rod, right?
Right. So the researchers needed a way to test what the babies inferred about that hidden space, and they used a technique called habituation.
Habituation.
Yeah. They let the babies watch this moving rod behind the box until they simply got bored and looked away. That's the habituation phase.
Okay.
Once the babies were bored, the researchers removed the box entirely and showed them 2 new test displays. One was a complete solid rod moving back and forth. The other was a broken rod, literally just 2 separate pieces with a gap in the middle where the box used to be.
Right, and in infant research, looking time is the ultimate metric. If they look longer at something, it means they're surprised by it, right? Like it's novel or unexpected.
Yeah.
So if they looked longer at the broken rod, it would mean they expected a solid one.
And that's exactly what happened. The infants looked significantly longer at the broken rod. They were surprised by the gap.
Wow.
This proves that when the box was covering the middle, their brains had automatically inferred that the 2 pieces were connected. Even at 2 months old, they understood object unity. They don't just see disjointed pixels of light, they mentally fill in the blanks to infer the whole, complete object.
Which bridges perfectly back to the fMRI findings. Whether they are mentally connecting the hidden pieces of a rod in the UCLA lab, or categorizing a jumping cat as an animate object in the IMAX scanner, these 2-month-old brains are engaging in really intense, complex problem solving.
They really are. They're actively organizing the visual chaos around them.
So what happens as these babies grow? Did the Stanford and Trinity researchers follow up on them?
They did, yeah. They actually brought 66 of those exact same babies back to the lab when they were 9 months old, and they put them back into the MRI scanner to watch the same videos.
Huh. Getting a 9-month-old to lie still sounds exponentially more difficult than a 2-month-old.
Oh, it requires immense patience from the research team, let me tell you. But they managed to capture the data, and they found that the identical brain patterns they observed at 2 months had grown significantly stronger and much more refined.
Really?
Yeah, the neural signatures separating living things from inanimate objects were now deeply entrenched. The brain engages in a process of pruning and strengthening, you see. It discards inefficient neural pathways while fortifying the ones it uses constantly.
So the foundational sorting folders they laid down at 2 months had become the sturdy, high-speed architecture of their 9-month-old minds.
That's beautifully put.
Yes. Well, let's bring this down to the living room floor. If you are a parent listening to this right now, holding a baby or watching a toddler, what is the practical application of all this data? Why does this matter for your daily life?
I think the most profound implication is a fundamental shift in how we view infancy. Your baby is not a blank slate, just passively waiting to learn how to speak or walk before their cognitive development begins. From the very first weeks of life, they are actively, hungrily categorizing the world.
So every interaction is raw data for those mental folders. Every high-contrast book you show them, every walk you take where you point out a dog or a tree.
Every single time you talk to them.
Yeah, their brain is just soaking it up and organizing it. You are literally providing the data they use to build a conceptual map of their entire reality.
It's a huge responsibility, but also incredibly empowering. And beyond that paradigm shift for parents, there's a massive medical application tied to this awake fMRI research, too.
Oh, right. Tell us about that.
By mapping what a neurotypical brain looks like at 2 months old, scientists are laying the groundwork for an incredibly early diagnostic tool.
Because right now, diagnosing neurodevelopmental disorders typically relies on observing behavior, which means waiting until a child is much older, right?
Exactly. Currently, conditions like autism or ADHD often can't be reliably diagnosed until a child is preschool age or older, because we have to wait for behavioral markers to show up in how they play or speak.
That makes sense.
But if we can map the literal blood flow and categorize the neural pathways at 2 months old, we could potentially spot atypical brain development years before it ever manifests in behavior.
Wow. And early detection changes the entire trajectory of support. Spotting atypical development at 2 months would allow for targeted interventions at the very beginning of a child's cognitive journey that could radically improve long-term outcomes for families.
It really could. It's not just about understanding how babies think. It's about revolutionizing pediatric neurology. We're looking at the potential to reshape how we support neurodivergent children from the very start. The lights are definitively on, and the cognitive machinery is working at full capacity from day one.
That is just phenomenal. We started this deep dive talking about that moment when you look into a newborn's eyes and wonder if anyone is home. I think it's safe to say the inner world of a baby is a bustling factory of cognition.
Absolutely.
But before we wrap up, I want to leave you, the listener, with one final lingering thought. It's actually a question prompted by Dr. O'Doherty, the lead researcher of the fMRI study. So we know definitively that a 2-month-old's brain fires differently for a cat than it does for a tree. It categorizes the living from the non-living.
The sorting mechanism is demonstrably there.
But do they actually know what a cat is? They have a mental folder for an animate object. But what does the concept of cat mean to a being that has never petted fur, never heard a meow, and never felt the weight of an animal in its lap?
Ray, it's such a wild concept.
So next time you're holding your baby and you see them lock eyes with the family pet, or just stare intently at a ceiling fan, ask yourself, what exactly are they categorizing right now? What silent, hidden meaning are they assigning to our world before they even have the words to describe it?
It is a beautiful mystery to ponder. The fMRI machine can show us the blood flow, but the actual lived experience of the infant mind is turning out to be deeper and far more brilliant than we ever imagined.
They are definitely not just cute, sleepy blobs.
Yeah.
Thank you for joining us on this deep dive. Keep wondering, keep exploring, and we'll see you next time.